Thanks everyone for being here, and I am Brian Argrow, chair of SMED Aerospace Engineering Sciences, and the director of the Integrated Remote and In-Situ Sensing Center. That's one of the CU Grand Challenge projects. So the building behind you here, there are some stats on it. 175,000 square feet, and we're using the roof. The roof is one of the prime's part of the real estate, and you can see other things there, including ITAR compliant offices and laboratories and other facilities. One of the things we want to do is encourage our industry collaborators and partners that we have these facilities, and we're looking forward to having you integrated into actually using some of those facilities, as well as hiring our students. So Hypersonics, we have one of the largest projects going right now with the Air Force. This project is a 5-year project. Started off at $7.5 million, but we just got a plus up of another $700,000 for this project. And the focus is to look at the stratosphere, where between approximately 80,000 and 120,000 feet, excuse me, and characterize what's going on in the stratosphere, and also to use that information to then inform simulations, and looking at how how vehicles would operate in the stratosphere. So we have a multi-university team, and the acronym HyFlights, hypersonic flight in the stratosphere. The research objectives are basically to look at identifying the characteristics of turbulence and particulates in the stratosphere. With hypersonic aircraft, one of the primary concerns is the stability of the boundary layer, and the tendency to transition from laminar to turbulent, because there are potentially catastrophic things that can happen if that transition is not understood. And so what is the role of turbulence, particularly turbulence that's being driven by things happening in the troposphere? So by weather, by orographic features, things like that are dumping energy via what's called gravity waves, and these are not the gravity waves from black holes. These are atmospheric gravity waves, and how they propagate into the stratosphere. So this is our multi-university team. Dave Fritz, for instance, is world-class in terms of atmospheric science. Graham Candler, one of the leaders in hypersonics simulation. You can see our CU Boulder team there also. And so the expected new capabilities for the Air Force, the reason why they're investing heavily in this project is, again, to quantify what's going on in the stratosphere in terms of particles and turbulence, and to be able to eventually develop a capability of forecasting. So you have, you launch from point A, you're going to need to get to point B. What are you going to fly through on the way there, and how do you manage maneuvering? And so that's the last thing you see right there. So these are the research topics, specifically looking at small-scale turbulence, because that's what's going to drive what's feeding into the boundary layer. Particulates, a volcano erupts. What effects does that, when the particles are in the stratosphere? Meteors come in and sprinkling particles. What does that do in terms of stability of the boundary layer? Also, there's a portion of this is focused on optical propagation. So lasers, other beams of energy in through the stratosphere. How does turbulence in particular affect the propagation of electromagnetic signals? This is how we're organized. 3 major efforts. The stratospheric measurements, we've already started that, so we're launching balloons. Back to the theme of IRIS, if you've heard me talk about this before, the goal of that center, of that program, is to fill the air gap between the ground and space with sensors and services. So if you heard me talk before, I was talking primarily about drones. Now I'm talking to you about balloons, in terms of we do what's necessary to get the instruments where they need to go to make the measurements. Atmospheric modeling, forecasting, and then the aerothermodynamics. So this is where actually doing state-of-the-art, and this is literally state-of-the-art hypersonics simulation. This is an example of some of the atmospheric modeling. I wanted to walk over there, but I guess I won't. Let's see if there's what you see on the right here is a actual satellite data showing gravity waves propagating from deep convection that's occurring over the Great Plains. So you can see Missouri, Oklahoma, Arkansas there. And further to the right is a simulation that was done by Dave Fritz and his group to simulate the effects of deep convection and how gravity waves then propagate through the stratosphere. We are actually going to combine this project this summer with a drone project that we have funded through the National Science Foundation, where we've been studying supercells and how they produce tornadoes. Well, one of the things that's of interest is these supercells actually will punch through the tropopause and create disturbances in the stratosphere. So while we have one of our teams will be underneath the storm, actually flying small drones in to study the formation of tornadoes, we'll have this Muri team, this high flights team will be on the periphery launching balloons into the stratosphere, looking at the disturbances that are being created by these storms as they form and evolve. So it's a really big deployment this coming this summer. So that's just more examples of simulation. This is a slide showing our colleague at Embry-Riddle who is developing a bus and balloon launching strategies to get our instruments into the stratosphere. And this is just some of the results that he's worked on. We use right now looking at a two balloon approach so that we get the instruments into the stratosphere, and we actually want to make our measurements as the instruments are coming down, because on the way up, the instruments are hanging in the wake of the balloon. And so your measurements are off. What we want to do is get into the stratosphere, pop one of the balloons, and then have a relatively slow descent where we can make the measurements. And we're looking at other strategies in addition to that. We built a high altitude simulation chamber for calibrating our instruments. We can simulate conditions in the stratosphere, and that what you see down in the lower right there, lower left, is a gondola from the first launch of some of our instruments with some of our German colleagues that happened last November. And so the Germans have already done some launching of fine wire instruments into the stratosphere, and so we're comparing our instruments against theirs. And that's some actual data there to the right. This is a plot of a particulate concentration profile in the stratosphere from 80,000 to above 120,000 feet that was done by our colleagues at the University of Minnesota. And ultimately what we're doing here is the idea is to make DNS simulations, but to feed the DNS simulations with realistic data or input that is based on measurements that we've made in the stratosphere. So we're informing the modeling and actually doing the simulations to investigate what causes the amplification of disturbances in the boundary layer that eventually will lead to separation or transition. And this is also a slide showing some of the first year results from our colleagues who are doing the optical propagation. Greg Reeker, who's leading this, he's doing a lot of things with frequency comb, laser optics, and everybody's after him to learn more about this, because the applications range from what we're doing in the atmosphere here to looking at what's happening inside of internal combustion engines. Schedule, I only put this up here to show that we're making progress in terms of, you can see we mapped our major efforts onto this 5-year program, and so we've hit several milestones already. And I want to conclude with one other slide. This is our effort from the ground up. We also are doing research from space down when we talk about hypersonics. And so this is a project we're doing with ULA, United Launch Alliance, and looking at the advanced cryogenic evolved stage that they are proposing to develop as part of this idea of developing a cislunar economy. And so these are actually Monte Carlo simulations, direct simulation Monte Carlo method simulations of their spacecraft doing aero maneuvering. So this is an aero braking that would be used to bring a space vehicle back, a spacecraft back from the moon, and using the atmosphere for purpose of braking and circularizing the orbit. So hopefully I was under 10 minutes.